Hi, we're PF200. I'm Whitney.
I'm Sandra.
I'm Amy.
I'm Nicole.
I'm Fernando.
And we're working on scaling down the Agua Clara plant from the big concrete plants that you know and love to ones that are about 1 liter per second, actually 0.67 liters per second for smaller rural communities.
So, with an estimated 2.5 billion people around the world lacking access to clean water, and a majority of them belonging in rural areas, PF200 could provide a great solution to this problem. PF200 is intended to be an easy-to-build modular water treatment plant that provides clean water to a small community of people. This could be a more practical solution, especially to smaller communities where it's not reasonable to fund and build a full-scale water treatment plant. With the success of a PF200, a small but impactful dent could be made in helping spread access to clean water.
So the work of our team this semester has been mostly finding the problems with the past iteration of this plant, and there are currently problems with the flocculation system, the sedimentation tank, and the filter. And we will talk more about what we are doing to address these problems shortly.
So the past designs of the flocculator involved using a long pipe that was contracted at certain points to achieve the necessary head loss for flocculation. But then in spring 2017, a possible new design was suggested where they would use PVC semicircles that would be threaded through a rod, and that would act like a traditional baffle. However, there were still some issues with the flocculator. Many of them involved being the high cost of PVC fittings and the short residence times. Because of the short residence times, that would mean plant operators would have less time to react to certain events in the flocculator, such as dirty water reaching the set tank. And based on these criteria, the PF300, which is now known as PF200, was in need of some improvement in the flexibility of the design. In particular, they would need to design a more efficient design for portable plants of different sizes. As of now, we're mainly focusing on redesigning the filter. So the majority of the redesign in the flocculator is designated for future work. However, we know there are still several constraints that we have to take into consideration. Primarily, one of them is being that it has to fit a large tube similar to the conventional flocculator with more traditional baffles. And we took a design that was from the CEE 4520 project of the flocculatorita. And with this design, we need to figure out how to keep the baffles in place. We're considering using threaded metal rods and stringing them through each baffle, or using some sort of system with slots. However, this will also depend on what material we are choosing for the baffles. And beyond the baffles, we will still have to decide what height the flocculator is to get the desired head loss and the number of collisions that are needed for flocculation to occur.
So the previous design of the sedimentation tank was a large pipe that was cut and then wheeled back together at an angle to support the sedimentation plates that allow the flock to settle on. And the sedimentation plates themselves were literally plates of metal slanted at an angle. And some previous versions in Honduras were actually plastic roofing tiles for this function. And there was a single jet reverser at the bottom of the tank to prevent flock from accumulating at the bottom. And finally, there was a flock hopper to remove flock. And so there were several problems we found with the old design. The slanted top of the tank was rather hard to fabricate, which kind of defeats the purpose of the PF200, as it should be easily shipped and fabricated on site by local workers. The flock hopper was also discovered to be too small, which led to flock buildup in the tank. And the bottom geometry of the tank was also rather hard to manufacture, as jet reversers were designed to be implemented in rectangular concrete plants rather than the circular tubing that the PF200 sedimentation tank was in. Some ideas we have to fix this is changing the geometry. So we're thinking of changing the circular pipe into a square tank, which would immediately solve fabrication problems, as now we can fit a square jet reverser at the bottom. And we're also considering using hexagonal plate cellars to limit the need to physically slant the tank itself.
So the PF300 filter has 4 main components: the entrance tank, the filtration system, the exit tank, and the backwash line. The distribution of flows can be seen on the image that you have on the right of your screen. And there were two main problems related to the design of the last summer. The first of them was that significant losses of sand were observed during the operation of the filtration system, and this happened in three main ways. The first of them was through the exit pipes, which was not supposed to happen because they have slits whose size is supposed to be smaller than the sand particles. Another way was through the entrance pipes, which was rather possible because their holes were larger, and also through the backwash line, which was also possible if the velocity of the upflow was too high. And also, the second and probably more important problem was that the filtration system never actually worked on the summer model. So a redesign has to be performed. Yeah. The aim of our team is to introduce gravity exclusion zones in the outlets, and the plan is to build a new full filter and test all the possible designs. The filter tank should be made of transparent PVC so that we can inspect the forward filtration and backwash processes and check that sand does not escape into the exit tank. The tank will have a rectangular shape, which will make fabrication easier, and also will reduce the costs. And the STARS exit outlet pipe has to be redesigned so that sand doesn't enter the exit tank. And the current proposal is to build pieces for the flow channels that are similar to the CAD design that you can observe. For the gravity exclusion zones. The team has worked on the new filter design considering the fastest flow conditions, which happen when the backwash process has just ended and the filtration process is starting again. An optimization process was carried out to determine the dimensions of the flow channels, and the team encountered situations in which we had too many variables and too few constraints. So we had to have several meetings and take several decisions to make those variables fixed and introduce new constraints so that a final design was obtained. A final design has been obtained, and we have already 3D printed 3 models. And the next steps are finding a way to fix those pieces to the filter tank and also to test the overall system.
So the fabrication part of this fabrication team so far has been the 3D printed flow channels that we've made. The different iterations are mostly based on the different dimensions of the filter tank that we decided to go with, the different hole spacings that we've calculated, and the thickness of the material. And we've stress tested these, and they seem to be ready to be put into an actual filter and used, but we haven't yet tested them in an actual like forward filtration or backwash setting. So we're not exactly sure if they work, but the calculations that we will show you in the appendix have informed these decisions.
So as you can see, there are many parts that need to be redefined for the PF200. We have chosen to start with the new filter outlet pipe, and then we'll move on to the flocculator and the sedimenter. For our future plans, we plan to start to fabricate and then test the proposed flow channel design, as Whitney was saying. And from there, we will begin to fabricate our final design and begin assembling the full filter setup. And then finally, we will be able to stress test the filter and determine if this is the best design.
So our calculations have been mostly the backbone of all of the decisions that we've made this semester, with some constraints based on ease of fabrication. The most recent calculation was to find out the total area of holes needed per branch based on head loss calculations. and also the number of branches and the angle that those branches should be at, which was decided based on the work of Stars Fine last year and some Excel solver methods about how to maximize the surface area of the sand-water interface.